Welcome back, everyone. Ready for another deep dive? Today, we're taking a trip to the utterly bizarre world of neutron stars.
They certainly are bizarre.
Yeah, and we're going to zero in on one particular mystery. Superfluidity.
It almost sounds like something out of science fiction.
It kind of does, like some kind of superpower, right? But this is real deal science, and believe me, way cooler than any comic book stuff.
Oh, absolutely. We're talking about fluids that flow without any resistance.
Like forever.
Like forever. Imagine a river that just never slows down. Crazy.
It really is. And to think, this might be happening inside a neutron star.
Which is already mind-blowing on its own, right?
Absolutely. We're talking remnants of a collapsed star crammed into a space smaller than, like, a city. And get this, a teaspoon of that stuff weighs billions of tons.
Billions. It's like a cosmic lab where matter is pushed to the absolute limit. And studying them.
Well, let's just say it's a challenge.
Because they're so incredibly far away. Incredibly. And that environment, it's beyond extreme. So scientists, they've been getting creative, trying to simulate these conditions, to understand what's going on in there.
And that's where AI comes in, right? I read about this new study using AI and neural networks to model neutron behavior. What's the deal with that?
Oh, it's a game changer. For ages, scientists have been trying to wrap their heads around neutron superfluidity.
And how do they even do that?
Well, there's this idea of Cooper pairs.
So pairs.
Yeah. Picture this. Neutrons, under immense pressure, they start pairing up, doing a kind of quantum dance.
Okay, interesting. But where does the AI come in? Does it watch videos of these neutron dances or something?
Not quite. This research used AI and these networks to simulate neutron behavior, way more flexibly than traditional models could. Basically, they built a virtual neutron star inside a computer.
Wow, a virtual neutron star. So they basically built an AI brain that could handle all that insane complexity, all those neutrons bouncing around.
Pretty incredible, right?
It is. But I'm curious, did the AI have to learn everything from scratch? About neutrons, I mean. Or did they, teach it some physics first?
That's a good question. It was kind of a mix, actually. They fed the model some existing knowledge, about how neutrons interact, but they also let the AI adjust and refine on its own.
So it's like a student starts with a textbook, but then does their own research.
Yeah, exactly. Yeah. And then there's the simulation itself, something special about how they modeled the neutrons.
Oh, tell me more.
Well, they introduced hidden neutrons into the model. And no, they're not wearing little neutron invisibility cloaks or anything.
Haha, phew, that was my next question.
Instead, think of them as mediators, helping capture those complex quantum interactions between the real neutrons. And this is where it gets really cool. By including these hidden neutrons, the model could let Cooper pairs form naturally.
Oh, so unlike before, they didn't have to force the pairing.
Exactly. So by adding that extra layer of complexity with the hidden neutrons, they made the simulation way more realistic, allowed the physics to just, play out.
Okay, that is fascinating. But how do we know these hidden neutrons aren't just a trick, to make the math work out? What evidence is there that they actually reflect something real about how neutrons behave?
It's a good point. The model's success really comes down to its ability to reproduce what we already know about neutron behavior. But the researchers didn't stop there. They also used it to predict the energy of neutron matter, specifically in those low-density regions of a neutron star. And guess what? The predictions lined up perfectly with calculations from traditional methods, the really complex, computationally expensive ones.
So they're not just making stuff up. The model's predictions actually match what we'd expect. That's impressive.
Very impressive. It suggests this approach, using AI and those hidden neutron mediators, could be a powerful tool for exploring other aspects of neutron star behavior. Things that are currently beyond our reach.
Okay, that's definitely exciting. But before we get into all of that, let's back up for a second. How does having a superfluid interior actually affect a neutron star? How does it behave differently?
Oh, it affects pretty much everything. How it cools down, its rotation, even those sudden changes in its spin rate. We call them glitches.
Glitches, like when my computer freezes and I have to restart it.
Well, sort of. In a neutron star, a glitch is a sudden shift in its spin. And we think these glitches are linked to the superfluid inside. You see, the superfluid doesn't have to spin at the same speed as the rest of the star. Imagine it like two parts, loosely connected.
Okay, I'm following.
So when there's a sudden transfer of angular momentum between them, boom, you get a glitch.
I see. It's like a figure skater spinning gracefully and then suddenly, whoosh, speeds up or slows down.
Perfect analogy.
Right.
And those glitches, they're one of the key pieces of evidence we have that superfluidity is really happening inside these stars.
Wow, so this AI model, by helping us understand superfluidity better, could give us a deeper understanding of those glitches, too.
Exactly. And that's just the tip of the iceberg. What AI can do for astrophysics, for understanding the universe, we're just getting started.
This is mind-blowing stuff. We've journeyed into the heart of a collapsed star, explored this crazy world of superfluidity, and seen how AI is helping us uncover these cosmic secrets. And this is just the beginning.
You know, it's amazing how AI is changing the game in scientific research. And what's really exciting is that all this new knowledge about neutron stars, it can actually help us understand basic physics right here on Earth.
Wait, really? I always thought of neutron stars as like these isolated things, exotic objects, completely separate from our world. How could studying something so extreme tell us anything about what's happening here?
That's a common misconception, actually.
Right.
While it's true, conditions inside a neutron star are extreme, but the forces at play, those fundamental forces governing how matter behaves, they're the same ones that work in the nucleus of every atom right here.
Oh, wow. So it's like we have this giant cosmic lab up in space, allowing us to study the building blocks of matter in ways we just can't do on Earth.
Precisely. This study, for instance, focused on low-density neutron matter. It's where these fascinating quantum phenomena like superfluidity emerge. And the insights we're gaining, they can be applied to other areas of physics too, areas dealing with similar quantum behavior.
So it's not just about those faraway neutron stars, then. This research could have ripple effects across multiple fields of physics. That's incredible.
It really is. And speaking of pushing boundaries, I think it's important to acknowledge the amazing team of scientists behind this breakthrough.
Oh, absolutely. I always love hearing about the people behind these discoveries. Who are the masterminds?
Well, the lead author is Bryce Four, a graduate student from Washington University in St. Louis. He worked with this international team of physicists from institutions like Ohio University, the University of Oslo.
Wow, a global effort.
It really is a testament to how collaborative science is these days.
It's inspiring, how scientists from all these different backgrounds come together to tackle these huge questions about the universe. Sometimes I think people have this image of a scientist working alone in a lab, like a lone genius or something.
Right, the classic image.
But in reality, science is a team sport. It's about sharing ideas, challenging each other, building on each other's work.
Couldn't agree more. And in this case, this collaboration led to a major leap forward. Not just in our understanding of neutron stars, but of matter itself, really.
And while we're talking teamwork, we can't forget the institutions and organizations that supported this research. Cutting-edge science like this needs resources, right?
Absolutely. This study was backed by the Department of Energy's Office of Science, the National Science Foundation, and a bunch of high-performance computing facilities. They provide the funding, the infrastructure. They're crucial for advancing scientific knowledge.
It's a good reminder that science is an investment in our future. Discoveries made today could lead to technologies we can't even dream of yet. Who knows, maybe this research on neutron stars will revolutionize materials, science, energy production, even computing. The possibilities are endless.
Absolutely endless, and that's what makes science so captivating. There's always something new to discover, some new mystery to unravel. It's a never-ending journey.
It really is. But before we get lost in the infinite possibilities, let's bring it back to this deep dive. What would you say are the key takeaways for our listeners about neutron stars, about this AI research?
Well, I think the biggest takeaway is the sheer power of AI for scientific discovery. We're seeing it used everywhere, from medicine to climate science, now astrophysics. It's letting us tackle problems that we used to think were just too complex.
It's like AI is giving our brains a super boost. And it's not about replacing scientists, right? It's about enhancing what we can do.
Exactly. And here, it's led to a breakthrough in understanding these incredibly dense, mysterious objects that have fascinated scientists for decades.
Neutron stars. And through AI, we're understanding this bizarre phenomenon of superfluidity better, seeing how it shapes these cosmic powerhouses.
Right. And it's not just about neutron stars themselves. As we discussed earlier, the implications go way beyond that. They could affect other areas of physics, maybe even lead to practical applications here on Earth.
It's amazing how it all connects. This study shows us that even the most fundamental discoveries can have these unexpected, profound consequences. It's like the line between theoretical research and real-world impact is blurring.
Exactly. It's like a chain reaction of knowledge and innovation. It's so exciting to think about where this research will lead us in the future.
I have a feeling it's going to be quite a ride.
Oh, I think so too.
Yeah.
There's one more thing I wanted to mention. We got a comment from a listener, Bahua Zhang, who brought up a really interesting point.
Oh, yeah, I remember that one.
They argued that, current physics, specifically the standard model, it has limitations. Even suggested some accepted theories might be, and I quote, blatantly talking nonsense. They were advocating for a different approach, something called topological vortex theory.
That comment definitely sparked a lot of discussion. And while we always encourage critical thinking, exploring different viewpoints, it's important to remember extraordinary claims need extraordinary evidence. The standard model, while not perfect, has been remarkably successful in explaining so much of what we observe.
Exactly. And while acknowledging limitations is crucial and searching for better explanations is key, any alternative theories need to be rigorously tested. We need solid scientific evidence to support them.
So while topological vortex theory might sound intriguing, we need to approach it with a healthy dose of skepticism until the scientific community has really vetted it. Science is a process of constant refining, revising. And through that process, we get closer and closer to a more accurate understanding of the universe.
Absolutely. And that's what's so exciting about science, isn't it? It's not about dogma or absolute truth. It's about constantly seeking knowledge, questioning assumptions, following the evidence wherever it leads.
Well said. Open minds, but also rigorous evidence. And speaking of evidence, I think it's time to wrap up this deep dive into the fascinating world of neutron stars and superfluidity.
It has been a pleasure exploring these topics with you and our listeners.
Before we sign off, a huge thank you to our expert for sharing such incredible insights. It's been truly mind-expanding.
The pleasure was all mine. And thank you to all our listeners for joining us on this deep dive.
It's easy to get caught up in all the new stuff, these amazing discoveries about neutron stars.
Right. It's so exciting.
It is. But sometimes I think it's good to take a step back, appreciate how far we've come, in our scientific journey.
I agree. It's pretty amazing when you think about it, how much we've learned about these incredibly distant, extreme objects.
It's mind-blowing. I mean, for centuries, they were just these tiny points of light. And now we're figuring out what's happening inside them, unraveling these mysteries.
It speaks volumes about human curiosity.
Yeah.
And ingenuity.
It really does. And it's not just the tech either, right? It's the people, those brilliant minds who dedicate their lives to understanding the universe, pushing the boundaries of what we know. Every new discovery, it's like another step forward.
Absolutely. When I think back to the early days of neutron star research, it's incredible how much our understanding has changed. There was a time when people didn't even believe they existed.
No way.
Oh, yeah. The theory, the idea of neutron stars, it was proposed back in the 1930s. But we didn't have actual proof until 1967, when pulsars were discovered.
Pulsars, those are neutron stars, right?
They are. But even then, it took a while for everyone to accept it, that these rapidly spinning supermagnetic objects were the neutron stars predicted by theory.
Science can be a slow process sometimes, huh?
It definitely can be. It's not always about those big aha moments. It's about slowly gathering evidence, refining our understanding bit by bit. And sometimes, new ideas, especially if they challenge what we think we know, they take time to be accepted.
That's so true. It makes you wonder what other revolutionary ideas are out there, just waiting to be discovered or accepted.
Exactly. The history of science is full of them. Ideas that were first dismissed, even ridiculed, but ended up changing everything. Continental drift, relativity, quantum mechanics, all met with resistance at first, but eventually the evidence was just too strong to ignore.
And that's what makes science so exciting, I think. It's not about clinging to what we think we know, but being open to new possibilities, questioning our assumptions, being willing to change our minds when the evidence points us in a different direction.
I couldn't agree more. And who knows what the future holds for our understanding of neutron stars. As our tools get more sophisticated, both for observing and for computing, we're bound to find even more surprises.
Maybe we'll discover entirely new states of matter, ones that challenge our current theories. Or we'll uncover these unexpected connections between neutron stars and other areas of physics. The possibilities are truly endless.
Truly endless. And that brings us back to that comment from Bahua Zhang, the one about topological vortex theory, and questioning the standard model.
Oh, right.
They might need more evidence to support their specific claims. But their bigger point about the limits of our current understanding, it's a good one.
It is. We have to remember that even our most successful theories, they're probably not the whole story. There's always more to learn, more to discover, more to question. The standard model has been amazing, explains so much. But there's still things it can't account for, right? Like dark matter, dark energy.
Exactly. And it's those unanswered questions that drive scientific progress. They inspire us to come up with new theories, design new experiments, to push the boundaries of our knowledge even further. Who knows, maybe topological vortex theory or some other theory we haven't even thought of yet will be the key to solving these mysteries.
It's an exciting thought. The universe is full of wonders, and we're only just beginning to grasp its secrets. Every new discovery opens up new possibilities, new questions leading us deeper and deeper into the unknown.
It's a journey that never ends, full of challenges and rewards. And that's what makes science so beautiful, don't you think?
Absolutely. Well, on that note, I think it's time to wrap up this deep dive into the incredible world of neutron star and superfluidity. It's been a truly amazing journey, and I hope you, our listeners, have enjoyed it as much as we have.
Thanks for joining us. And keep exploring the universe with that same sense of wonder and curiosity.
Until next time, keep those brains buzzing. We'll catch you on our next deep dive.